All right, welcome to Energy. So, you guys learned a ton of definitions last year. What kind of energies do you know? Kinetic. What's kinetic energy? Energy moving. Good. What does kinetic energy depend on?
Velocity and mass.
Speed and mass, right? Is it speed or is it velocity?
Speed. It doesn't matter because you're squared.
Yeah, that's right. It's squared, right? If you square something, it becomes an absolute value anyway. Wait, what does that imply about kinetic energy?
It's always positive.
It's not a vector, right? Energy is not a vector. It's only a scalar. All right, good. Oh, that's interesting. Can you have negative energy? Negative kinetic energy? Why can't you have negative kinetic energy? Mass can't be negative, right? And if you square velocity, that can't be negative either. So kinetic energy is always a positive quantity, and that has kind of some interesting ramifications to it. What other kinds of energy do you know? Potential. What kinds of potential? MGH. Can that be negative?
Yeah.
Why? Yeah, because if you have a zero height level, assuming you're using MGH, you can go below that height and therefore have a negative potential energy. So let's say I have a 1 kilogram jug of water sitting right here, which I think this is actually a little less than a kilogram, but whatever. Let's imagine it was 1 kilogram. Sitting on the table, how much potential energy does it have?
You need to define a height of 0 first.
Right, so it would be m times g times h, right? So what's m? 1. What's g? 9.8. What's h? It depends. Who says h is 0 sitting on the table? 0 height. Who says h is about 1 meter because, well, that's about 1 meter off the floor? Okay. Who says h is like 20 feet because it's like 20 feet above ground level right now? Who says h is about 4,000 miles?
Well, why not?
That affects
Center of the earth, right? Who says h is about 93 million miles?
Gravity doesn't affect it.
Oh, there's no gravity between us and the sun?
Well, there is. The acceleration of gravity is different, though.
Ah, so what you're saying is MGH doesn't work if G is not constant. I agree. All right. But the other point I'm getting at is that the height depends on your reference levels. All right? And we'll get a lot more into that later. All right? But for now, just understand if we're using MGH, gravity, G has to be constant. Yes?
What happens if, what can we do with G?
We have ways of dealing with this.
Step right here.
Yes. Yeah, we're going to do a little bit of calculus with it, and we're going to do a whole unit on it later on, towards the end of the calendar year. So we got gravitational potential energy. What other kinds of energy do we have? Springs. Yes. Can you store energy in a spring? Yeah. What was the relationship you used last year? 1/2 kx squared. What was k?
Spring constant.
Spring constant. If you came up with like a physical description of what k was, what would you say? Yeah. How stiff it is. So you agree that the stiffer the spring, the more energy gets stored if you pull it back a certain distance? All right. And then what was x? Distance from not from equilibrium, from unstretched.
Oh, yes.
Distance from unstretched is x. And that's going to be super important here in a little bit. All right, so here we go. What's work?
Force times distance
Interesting. A place where you get paid. So are you doing work right now? So so does anyone ever have parents who say like, you know, you don't know what real work is? Do you ever get that? Anyone ever? Raise your hand if you ever hear that.
It's like that one.
No?
It's
Okay.
like that one show. Like the force speed equal to mass times acceleration.
What?
No. There was one GIF and it's these two people and they're like made a force speed and then the other guy finishes and he's like equal to mass times acceleration.
That's right. That's right. All right. So, what is work? Well, work is this idea in physics. It has a very specific definition, and let's see if we can demonstrate it here. Once upon a time, I think that if you had regular physics, I showed you a picture of what my first car looked like. It was a 1979 Honda Accord CVCC.
We can guess.
Awesome car. Great car. It was like a nice rust brown, mostly because of the rust.
By intention.
Yeah, and it was a great car. This thing was just a beast. It was like maybe a little bit bigger than one of these tables, and like you could fit like 2 or 3 of your friends in the back, and it was awesome. It was a great little car, and unfortunately, when I had it, it was a little old. And which meant that I'd have to go out to the parking lot sometimes, and I'd find that my car wouldn't start. What do you do if your car doesn't start?
Jump it.
You could either jump it or you could push start. Has anyone ever push started a car before? Oh, no. Okay, so yeah,
See if it starts.
it really only works if you have a manual transmission, not an automatic. So what you do is you put your car in neutral. Somebody sits in the driver's seat. You put it in neutral so it's out of gear, and then you get like 3 of your biggest friends, and then they get behind the car and they start push, and then you pop the clutch and go, and it goes. Okay, so you get like 3 of your biggest friends, and you push, and they go. And then push, and then the car goes. When you pop it, and then the car goes, and that's fun, and it works. And I had to do this all the time. So the question I have for you is, what way were my friends pushing the car? Forward. What way did the car go?
Forward.
Was that positive, negative? Was that positive work or negative work that they did on the car?
They did positive work on the car.
They did positive work on the car. How come?
Because they were pushing it.
The force was forward, and the displacement was also forward. So what's the angle in between those 2 vectors? 0. So what's cosine of 0? 1. Positive or negative? Positive. Okay, so, all right, so what matters is the angle in between those 2 vectors, right? All right, fine. Different story, different day, towards the end of the senior year. Our high school was up on a hill, and because it was up on a very steep hill, it was on like 7th Avenue, and sea level was down here, right? And so half of the streets run level, horizontal, and then half of the streets are on a hill, right? All right, so you had a 50% chance of being able to park on level ground, which means 50% of the time you weren't on level ground. So I would go park my car, and honest to goodness, I'd come out sometimes and my car was rolling downhill. And I, no! And I go run after it. You get to the car, and what do? I'm like, right? To stop the car from rolling down. It's a small car. So what way do I push the car? Up. What way does the car roll?
Down.
Down. What angle is that? That's 180 degrees. What's the cosine of 180? Negative. So positive or negative work?
Negative.
I am doing negative work on the car. Does that make sense? All right, fine. After a few times of this, I get smart, and I'm like, there's no way I'm getting below the car. That's stupid. So what do? I go to the side of the car, see it rolling downhill, and push sideways. Which way does the car roll? Downhill. Which way am I pushing? Sideways. What kind of work am I doing on the car? None. How come? Cosine of 90 is 0, right. So if you're pushing it all in the direction of the way it's going, that's positive. If you're pushing away from the direction it's going, that's negative. And if you're pushing perpendicular, that's 0 work. Good? All right. So here's another one. If I push the car forward and the car goes forward, what's happening to its kinetic energy? It's increasing. How come? Because it's speeding up, right? So if the net force is in the same direction as the motion, then speed's going to increase, right? Okay. This is a little something called the work energy theorem. Ever heard of it?
Yes.
Okay, what's the work energy theorem?
The change in your energy. The change in energy is equal to the work. Work equals change in energy.
Work
Yeah.
changes kinetic energy. That's it. Work changes kinetic energy. If net work is done on something, guess what?
There's a change in kinetic energy.
The kinetic energy is going to change. By how much?
How much work you do?
However much net work was done. So if you do 10 joules of net work, how much is the kinetic energy going to change by?
10 joules.
10 joules. All right, if you do negative work, what's the kinetic energy change going to be?
Negative.
Negative. All right, good. So, example, car comes rolling downhill, and I go like this, right, and I push backward at it. And let's say I'm doing, the total work on it is negative. What's happening to the speed of the car? Slowing down. Does that make sense? And in the third case where I'm pushing perpendicular, yeah, constant speed. I'm not affecting the speed of the car at all. All right, good. Now here's the important thing about the work energy theorem. It turns out that it's net work. What's that mean? What's the net mean? Work due to all of the forces on it. So if there's a car rolling downhill, is there just one force on it? No. What's the free body diagram look like? Yeah, friction up the hill, gravity, which is straight down, and normal, which is kind of diagonal because it's perpendicular to the hill, right? Now, if the car is rolling at a constant speed, how much is its kinetic energy changing? It's not changing, so how much net work is being done? None. Does that mean the work being done by gravity is 0?
No.
No. What's it mean? The work done by gravity plus the work done by friction force plus the work done by normal force is all 0. So is gravity doing positive or negative work? Gravity's doing positive work because it's kind of at an angle kind of in the direction of motion, right? And is friction doing positive or negative work? Negative work, right? Because friction is against the direction of motion. What about the normal force? Positive or negative work?
0.
Who says normal force is doing positive work as the car's rolling down the hill? Who says it's, yeah, it's perpendicular. So what kind of work is it doing? None. So gravity does positive work, friction does negative work, and normal force does no work. And what's the net work being done if it's rolling at a constant speed?
0.
0. You guys got all this? All right, cool. Law of conservation of energy, I think you guys know that. Do you guys know it? Most important law in the universe. Did you know that? All right, good. Nothing's for free. All right. Okay. So last year's definition, work is that, FD cosine theta, which is great if the angle is constant or if the force is constant, right? But what if the angle's not constant? What if you're walking along the line and getting pushed in all sorts of weird directions? Or how about this? A roller coaster goes down a hill and then bottoms out at the bottom. Is the angle between the roller coaster's motion and gravity constant? No, it changes because when it's steep, the angle is really small, and when it's at the bottom, the angle is 90 degrees, right? So how do you calculate the total amount of work done by a roller coaster that's reaching the bottom of the hill and leveling out? What do you have to do? You have to integrate. You have to add up all the little bitty bits of work that's done every centimeter as it drops, right? All right. So, here's what that looks like. The integral of work is you take all the little pieces of force times all the little pieces of distance times all the cosine thetas all the way down the roller coaster track as the roller coaster track changes its angle. Add all those up and you get the total work for that chunk of roller coaster. Total work by gravity. Does that make sense? All right. So what that looks like is an integral sign, right? Looks like that right there. All right. So in order to do that, well, let's see. You got to know something called the dot product. Have we talked about dot product yet? Raise your hand if you've heard of the dot product. Raise your hand if you haven't heard of the dot product. All right. If you're in multivariable, you've heard plenty. Yes. Yeah. It turns out FD cosine theta is actually a what? It's a dot product. It's really the F vector dotted with the D vector. All right. So this year, shoot! I forgot my lead into this. Shoot! How do you multiply two vectors? How do you multiply, say, for example, 2 miles north times 4 miles east?
Times 4, and then in the direction northeast. Oh wait, no.
No, that's how you add them. How do you multiply them?
You add them together. Dot product.
Yeah, there's actually two ways. One way gives you a scalar answer, and the other way gives you the vector answer.
You multiply the components or you do them, right?
Yes. Dot product is the one we're going to talk about first. Dot product is you multiply a vector times a vector, and you get a scalar answer.
Bless you.
So an answer without direction.
Oh, those are cross products.
All right, yes, we will do cross products as well.
Wonderful.
All right.
Matrices.
Two ways to calculate a dot product. Here we go. One way is AB cosine theta. The other way is the component of A in the I direction times the component of B in the I direction, plus the component of A in the J direction times the component of B in the J direction. And you add them up. Here's the kind of the stuff that you already know. Dot product is max when the angle is 0, 0 when angle is 90 degrees, and max negative when angle is 180 degrees because of cosine, right? All right. Let's see what else. Is there anything interesting on here? Oh, yeah, this is neat. What if I gave you two random vectors? An A vector and a B vector. And I want to know the angle in between those vectors. How would you tell me the angle?
If it's 0, it's perpendicular. That
You
product
do
is
the
0.
inverse tangent.
What if I gave you the vectors in 3 dimensions? Like, I pick a random direction in this room and another random direction in this room. And I gave it to you in terms of I hat, j hat, and k hat. Could you tell me the angles between them? The angle between them. 2 months ago I could have. Well, here's the thing.
More than that.
We know that AB cosine theta has to equal this thing right here, this AI BI plus AJ BJ, right?
Yeah.
So if those two equal each other, you can get a number from this one and set it equal to this, solve for theta.
Okay.
Does that make sense?
Yep.
All right, so let's try it. Let's say A is 2i plus 3j, and I is negative 1i plus 4j. That means A is this way and B is that way, right? If AB cosine theta is equal to AI BI plus AJ BJ, what's the magnitude? How do you get the magnitude of A? What is the magnitude of A? Yeah, it's 2 squared plus 3 squared square root. And the Pythagorean theorem, right? Do that times cosine theta equals, what's AI BI? 2 times negative 1 is negative 2, right? AJ BJ is, oh my gosh.
Yeah.
Oops.
Wow.
I just
Wow, that's awesomely stupid. You see the math mistake?
You added 3.
Oh, that's awesome. That right there is supposed to be 12. Fix that in your notes, please. Wow.
Next number should be, I'm not sure what that
So this should be 10.
It's around 1. It's a little less than 1. It's like points.
So what does that angle come out to be?
Wait, that's not the angle.
What's that angle?
Wait.
Inverse cosine of 0.87.
I know. I'm trying to do this. It's 28.7.
28.7 degrees, so about 29 degrees. Does that angle look like about 29 degrees?
Sure.
No.
Well, yeah, well, it's
I mean,
cute.
it's-
It's definitely acute, right?
It
Alright.
look like 64.
Yeah. Oops. Sorry.
It could be 64.
So anyway, that's good to know. So that's kind of a cool thing. The dot product is a really neat way to get the angle between two vectors. All right, so let's move on. Back to physics. Work is a dot product of force and displacement. In other words, all that stuff. If you're in the same direction, positive work. Perpendicular, 0 work. Opposed, negative work. Work energy theorem. The net work done on the object changes the kinetic energy. So here's all the examples of the car on the hill. All right. If you apply a force opposite the direction of motion, that's negative work. This is positive work, and this is 0 work. Good? All right, moving on. Then net work is the sum of all the forces work. So if the car is speeding up, what do we know about the net work?
Positive.
We know gravity is doing more positive work than the applied force is doing negative work, right? Yes?
If you were jumping on top of the car, would you be doing work technically?
Oh, interesting. If you're jumping up and down on top of the car. So let me go back to the picture. So you're saying
Okay.
you're going boing, 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 right?
So would you be doing positive work?
Is the car moving?
Yes.
Which way?
Uh,
Down the hill?
Yeah.
So every time you hit the car, you're applying a force that's straight down, right?
Yeah.
And the motion is like that. So you've got an angle that's an acute angle.
So you're doing positive.
So you're doing positive work.
So
All right.
But you're applying more friction to.
Yes, you are also giving it a little bit more friction because you're getting the end a little more normal force. But I would say overall you're probably doing positive work. You're going to help the car down the hill rather than helping it back up the hill, right? Which would make no sense. All right. Work is a line integral. Okay, this is where the math gets fun. Here's that roller coaster I was talking about before. The total work done from the top of the hill to the bottom of the hill, in order to get that, you've got to do the total work for this little piece, plus this piece, plus this piece, plus this piece, plus this piece, plus this. Means you got to add them all up, right? That's that little summation. But we know that summation, if you're doing it a whole bunch of times, just replace it with an integral sign. All right? The total work would be F dot dr added up. All right? Because each little piece of work is F dot dr. All right? So the total work is integral of F dot dr. This is called a line integral. Any guesses why it's called a line integral? All the multivariable people. Why is it called a line integral? Because it goes along the line. All right. It's called a line integral because it follows it. But note that it's a curved line. It's not a geometry line, which are straight. All right. That's right. Since work is an integral, it's also the area under the F versus R curve. So if we wanted to figure out the total work done in this picture, how do you figure that out? Area under each of those little pieces, and you add them all up. All right? And that is it. Nice job, guys.